James will present Decimal Tutorial 4, Part A. All we need to do is write that number correct to 3 significant figures. In order to write that number to 3 significant figures, we will first locate the third digit in order of significance by counting from the left. And at the left we will find the most significant digit. So we begin with the most significant digit, and as we count we are decreasing in significance, going all the way down to the third significant digit. Check the digit that is next in order of significance, and that digit that is next in order of significance to that third significant digit, we will find that to the right. So if we want to find the digit that is next in order of significance going down, then that digit will be located to the right. What is the purpose of doing that? The digit is 8. 8 is greater than or equal to 5. We add 1 to 6. We will add 1 to the third significant digit. And why do we do that? Because if the one next in significance is greater than or equal to 5, which is 8 in this particular case, which is definitely greater than 5, we will add 1 to the digit in question, which is this 6, the one in the third most significant position. 6 plus 1 is equal to 7, and the other digits to the left are not affected and return as they are. 477. Can that be right? We do not imagine that a number in the thousands can be approximated to a number in the hundreds. In order to return the number to thousands, we need a place holding 0. This number 4,768 we are approximating. That's what we do when we write a number correct to a specified number of significant figures or decimal places. It is a matter of making an approximation. Therefore, when we are through, the value or relative size of the number has to be maintained. Therefore, we need to have a place holding 0 here in order that this number will return to the thousands, because the original number is within that range. So there is our place holding 0. That, what do we have here? In order to return the number to thousands, we need a place holding 0. I have been explaining how problems may be solved without the use of the calculator, and now we are at another one to which we will do the same. Both multiplicand and multiplier have 3 digits, and it now seems that we are at the place where multiplying by 3 digits in turn is inevitable. Wrong. So it is not unavoidable that we should multiply by 3 digits in turn, although it appears to be like that. We are multiplying this by this. 0.428 by 2.75. 1, 2, 3 digits. 1, 2, 3 digits. I am saying I am making an attempt at this problem, solving it without the use of a calculator. And if we are multiplying, some students, candidates, may stick slavishly to a particular form or a particular method as long as the numbers have a particular appearance. But that is not the case. We do not have to stick slavishly to anything in mathematics. There is always an alternative. And life is like that. Sometimes it may be more difficult to travel to work on the traditional route. The traditional route may be shorter, maybe a smoother road, but maybe on a particular day there's a serious accident, or maybe some criminal tried to escape from police custody and they decide to have a roadblock or something. We may find that the traditional route may be on a particular day not so easy to take. Therefore, it may be on that special occasion better to take the alternative route, and that is what we are about to do. The numbers are perfect for mental operation, and we definitely do not have to use orthodox multiplication to arrive at our answer. 2.75 is equal to 2 3/4. To find 2 3/4 times a number, we will need to find 2 times the number and 3/4 of the number and add the two results together. So 2.75 turns out to be maybe a lot easier to multiply by than we imagine. All we need to do is take 2 times this number and take 3/4 of this number and add the result together. Then we have what? 2 3/4 of the number. And we will do that very soon. So now let us take 2 times 428. We don't even have to do it digit by digit. We may proceed like this. 2 times 28. 2 times 28 is 56. 2 times 28 is equal to 56. Write that down. Then we say 2 times 4 is equal to 8. Write that down. And it is as easy as that, multiplying by 2. Surely, it should not be beyond anyone at the CXC CSEC level to understand that 2 times 28 is 56. Maybe one might want to say 4 times 14, because 2 times 28 is the same as 4 times 14. Or we may even go a little bit further. 8 times 7, and that's equal to 56. But surely 2 times 28 is equal to 56 should not be beyond anybody attempting the CXC CSEC examination. Well, if it were the case before, now we are sure that it is no longer the case, because we know that 2 times 28 is equal to 56. We would have learned that from the present video presentation. Now we say 2 times 4, and that is equal to 8, and that is all there is to it. Now we need 3/4 of 428. What do? We say 4 into 4, or a quarter of 4, is equal to 1. Right here. So a quarter of 4 is equal to 1. And a quarter or 4 into 28. We may say a quarter of 28 or 4 into 28. That's equal to 7. But before we just write 7 down, remember, in order to say 4 into 28, we have to say 4 into 2. We can't. And then 4 into 28 is 7. So we say 4 into 4 is 1. 4 into 2, no whole number of times. And then 4 into 28 is 7. So remember that before we may say 4 into 28 is equal to 7, we first have to say 4 into 2 is equal to 0. And I am emphasizing, when we say 0, we are meaning no whole number of times, because we know that 4 into 2 is a half, but for the purpose of that long or short division, we are working mainly with whole numbers, so we say no whole number of times. That is what the 0 is for. And I am sure that it is not so difficult to see that 3 sevens 21 and 3 ones 3. So 3, 2, 1 right there. So 3 sevens 21 and 3 ones 3. So we have 321. It's not difficult to see that 107 times 3 is equal to 321. And what do we do? Well, surely the same thing that we said initially that we would do. Find 2 times 428 and then find 3/4 of 428 and then add the 2. So we have 6 plus 1 is equal to 7. 5 plus 2 is also equal to 7. And then finally 7 11, 8 plus 3 is equal to 11. We know that 25 and 4 are related numbers. Also, we need to maintain the presence of mind that we are not really multiplying 428 by 2.75, but we are actually multiplying 0.428 by 2.75. There is no doubt that the digits that we have here are correct, and these are the digits that we have that we are just transferring from the previous slide. Right, so there is no doubt that these digits that we have here are correct. However, we need to be aware that if we are multiplying numbers, one ending with 5 and the other with an even number, we will have at least one trailing 0 in the result. On this occasion, we are multiplying a multiple of 4 by a multiple of 25. We will therefore have 2 trailing zeros. And I am sure that no one will have any difficulty with this statement that we have right here. If we are multiplying a number ending with a 5 by a number that ends with a whole number, then the answer should end with at least 1 0, because we know that 5 2's 10, that number ends with a 0. Then we know 5 4's 20, 5 6's 30, 5 8's 40. So we are sure that we will have at least a single trailing 0 right there. We are also saying, additionally, if we are multiplying a multiple of 4 by a multiple of 25, then we will have 2 trailing zeros, and we will take a look at that on a subsequent slide. So we will take a look at the reason for this on a subsequent slide. A reason for what? Looking at the reason why when we multiply a multiple of 4 by a multiple of 25, the result will have 2 trailing zeros. The answer, which is this one, the complete thing with the 2 trailing zeros, the answer will have the same number of decimal places as the total number of decimal places of the multiplicand and multiplier together. We will count those decimal places. When we multiply two numbers, the number of decimal places that we have in the two numbers that we multiply is equal to the number of decimal places in the answer. So let us count those. 1, 2, 3, 4, 5. So there we have 5 decimal places. The answer that we have will also have 5 decimal places. The answer will therefore have 5 places of decimal. In a whole number, the decimal point is assumed to be at the extreme right. We will begin counting from that position. So in a particular number, if we do not have any decimal point, meaning that we do not have a fractional part, and we do not have a fractional part expressed as a decimal fraction, then in that particular whole number, the decimal point is assumed to be at the extreme right. And there is where we will begin counting our 5 places of decimal. 1, 2, 3, 4, 5. So that is what our answer will look like. Zeros that trail a decimal point do not affect the value of the number. So zeros that trail a decimal point do not affect the value of the number, and they are gone. We may write the answer correct to 2 significant figures. We will begin doing that by locating the second digit in order of significance by counting from the left, and at the left we will find the most significant digit. So we start to write, whenever we are writing a number correct to a particular number of significant figures, we start counting our significant figures from the left, where we will find the most significant digit. Well, sometimes in a decimal fraction, we will start at the leftmost non-zero digit, but we do not have a decimal fraction that is accompanied by a 0 whole number part. Therefore, we may just go straight ahead. 1, 2. That's the second most significant digit, and that is the one that we have a focus on at the moment. Check the digit that is next in order of significance, the one that is located to the right. There we go. That is the one that we are checking. The digit is 7, and 7 is greater than 5. Because it is greater than 5, if it were equal to 5, we would still add 1, because if it is greater than or equal to 5. So the digit is 7, greater than 5, we will add 1. to 1, which is the digit in question. 1 plus 1 is equal to 2. The other digit to the left is not affected and return as it is. When rounding numbers, if the digit next in significance to the digit in question is greater than or equal to 5, then 1 is added to the digit in question. In this particular case, the digit in question is the second significant figure, which is this one right here. This is the second digit in order of significance. That is the one that we are focusing on because we are writing correct to 2 significant figures. And if the one next in line is greater than or equal to 5, we add 1 right here. It is 7, which is actually greater than 5. Therefore, we add 1 to this one, and that is where we got this 2 from. The other digit is not affected, and we have it returning as it is. Finish up by writing the answer in standard form. .177, and we need to write that in standard form. The number need to have 1 non-zero digit to the left of the decimal point. This number needs to have, the entire number needs to be expressed in a form in which it has only 1 non-zero digit to the left of the decimal point. As a matter of fact, the form that it is in presently is the one required of the standard form. The number as it is satisfies that requirement. There is therefore no need to multiply or divide by any power of 10. So no need to adjust this number in any way, because the decimal point is at the position relative to the other digits as required of the standard form. We may therefore treat the number as if it is multiplied by 10 to the power of 0. Therefore, we have 1.177 times 10 to the power of 0. As much as 0 may stand for no adjustment in the decimal places, we know that 10 to the power of 0 is equal to 1. As a matter of fact, any number raised to the power of 0 is equal to 1. Therefore, the result is actually 1.177 multiplied by 1, and that is equal to 1.177, as any number multiplied by 1 is equal to that same number. As much as we have agreed from the beginning that there should be no adjustment to the number, multiplying the number by 10 to the power of 0 is actually saying that there's really no adjustment to the number, because 10 to the power of 0 is equal to 1. As a matter of fact, any number raised to the power of 0 is equal to 1. Therefore, 1 multiplied by this number will be equal to that same number. Let us take a look at the reason why the answer should have 2 trailing zeros. We said that we would do that eventually now we are doing it. Take a look at the reason why the answer should have 2 trailing zeros. There is the original problem. 0.428 multiplied by 2.75. If we consider the numbers without the decimal places, we should recognize that the first one is a multiple of 4 and the other one is a multiple of 25. Well, we have made use already of the fact that this number is a multiple of 4. But it is clear, and as a matter of fact, I can remember discussing on previous tutorials that a number like this should be a multiple of 4 because the 100th, well, we are assuming or we are treating this number as if it is a whole number, just for clarity and for manipulation. As usual, whenever we do such a thing, we always make the adjustment to the decimal places in the end. So we are saying we are treating this one as if it is 428, and we know that the hundredths part of a number is a multiple of 4 because 100 is a multiple of 4. So the figure in the hundredths position will cause the number to be a multiple of 4. Also, we know also that 28 is a multiple of 4. Therefore, if this were not 428 but 528, this would still be a multiple of 4 because this 28 is a multiple of 4, and whatever we put in the hundredths position does not matter because 100 is a multiple of 4. So as long as this is a multiple of 4, it does not matter what number we have here. However, this 4 also is a multiple of 4, so that makes life even better for us. So we are sure that this number is a multiple of 4. Apart from this analysis, we are saying, as a matter of fact, we divided the first one exactly by 4 on a previous slide. So we did that on a previous slide, so we are even better off because we actually used it in that fashion as a multiple of 4. What about the other one? How do we know that the other one is a multiple of 25? Which is this one. How do we know that 275 is a multiple of 25? And we are treating these numbers, I'm reminding all that we are treating the numbers as if they do not have any decimal point. So how do we know that 275 is a multiple of 25? All of those numbers, 275, 325, 950, and 1200, all of those numbers are multiples of 25. Why? The multiples of 25 are evenly spaced within 100. Therefore, any number that ends with 25, 50, 75, or a 00 is a multiple of 25 because within 100 the multiples of 25 are evenly spaced, 25 units apart. We may therefore identify 275 as a multiple of 25. So any number that ends with a 25, a 50, a 75, or a 00, that number is a multiple of 25, and we know that this number is already a multiple of 4. So we are saying 1 is a multiple of 4, 1 is a multiple of 25. When we multiply the two numbers, we get 100. Therefore, any number that is a multiple of 4 and is also a multiple of 25 has to be a multiple of 100. And all multiples of 100 end with a 00. Therefore, any number that is a multiple of 4 and a multiple of 25 is also a multiple of 100. I hope that no one needs any special lesson to identify a number that is a multiple of 100. As we all know that multiples of 100 end with a double zero. Therefore, the number that we had being a multiple of 4 and a multiple of 25 must be a multiple of 100. All multiples of 100 end with at least a double zero. Therefore, we are sure that the number, the result of multiplying these two numbers should end with a double zero. So consequently, when we multiply a multiple of 4 and a multiple of 25, we will get a number that ends with a double zero. That is the reason for including the 2 zeros at the end of the number 1177 when we multiply 428, a multiple of 4, by 275, which is a multiple of 25. That is the result that we would get. Therefore, after we have gotten our digits, we need to include 2 trailing zeros, which will make this a multiple of 100, caused by the fact that we are multiplying a multiple of 4 by a multiple of 25. Finish up by writing the answer in standard form. Let us write that number in standard form. The number needs to have one non-zero digit to the left of the decimal point. Count the number of places by which the number has to be increased or decreased. Just one. One alone. The number is increased by 1 place of decimal. The number is therefore multiplied by 10, or 10 to the power of 1. We need to recover the original value of the number by dividing by 10 or multiplying by 10 to the power of negative 1. A number that initially had no non-zero digit to the left of the decimal point is called a small number and will be accompanied by a negative power of 10. So any number that has no non-zero digit to the left of the decimal point is called a small number, like a number that starts like this, 0 point. Any number that starts like this, 0 point, is a small number. And in the end, if you write that in standard form, it should be accompanied by a negative power of 10. We may write the given number correct to 2 significant figures. Locate the second digit in order of significance by counting from the left, and at the left we will find the most significant digit. When we say the left, we mean the first non-zero digit that is located at the left. Begin counting there, and that is the second most significant digit. Check the digit that is next in order of significance, and that is the one that is located to the right. 0. The digit is 0, which is less than 5. 1 is not added to 9. The other digits to the left are not affected and return as they are. When rounding numbers, if the digit next in significance to the digit in question is less than 5, then 1 is not added to the digit in question. In this particular case, the digit in question is the second significant figure, which is the 9. The one in the second most significant position is the one in question. We check the one to the right of it. If it is greater than or equal to 5, we add 1 right here. In this particular case, it is not greater than or equal to 5. It is not equal to 5 and it is not greater than 5. We do not add 1 to the digit in question, which is this 9 that we have right there. Shame on the candidates who subtract before performing the division operation, or even worse, before squaring 11.2. As we all know that division takes precedence over subtraction. So may even cry shame on the examiners for enclosing the division operation in brackets. Operations that are enclosed in brackets take precedence over all. Therefore, additionally enclosing the operations that take precedence over subtraction in brackets unnecessarily reduces the difficulty of the problem. Why should candidates not be allowed to demonstrate a knowledge of the simple fact that multiplication and division take precedence over addition and subtraction? We will square a number in the usual fashion by multiplying it by itself, or multiplying two occurrences together. The number 11.2 does not have to be a candidate for triple multiplication because of its 3 digits. We may use 2, then 11, or 12, then 1. So these numbers that we are multiplying, which is of course 11.2 multiplied by 11.2, we do not have to say multiply by 2 first, then multiply by 1, then multiply by 1. The problem, therefore, does not have to be a candidate for triple multiplication. What do? We say either multiply by 2 and then multiply by 11. We know our 2 times table and we know our 11 times table. Or we may take these 2 digits first, multiplying by 12 and then by 1. So we may use 11.2 or 12.1. I am opting for 12.1 because multiplying by 1 is easy. Any number multiplied by 1 is equal to itself. So 12 is easier because multiplying by 1 is equal to the same number that you are multiplying. So let us begin. 12 twos, 24. What do? Write the 4 and carry 2 to the more significant position. Then we go straight ahead and not say 12 times 1. 12 times 1. We know 1211 already. 1211 is 132. That 132 added to the 2 that was carried, we get 134. And we'll just write that down. Therefore, there we have 1344. But not quite, because in the end, we will have to make use of these decimal places. Then what do? We will now multiply by 1, the digit of greatest significance in the number. So 1 is what we are multiplying by, and that is the digit of greatest significance in the number. Remember that we multiplied by 12 first, so we have this 1 to multiply by next, which is, of course, the digit of greatest significance in that number. 12 has 2 digits. Therefore, the least significant digit of the answer obtained by multiplying by 1 will be 2 digits greater in significance than the least significant digit obtained by multiplying by 12. We will therefore include 2 placeholding zeros. Notice where this one is. If we start here, 1, 2, 3. Notice that this is in position 3. This is in position 1. Therefore, when we start our answer using 1, it should be 2 significant figures greater than where we started when we multiplied by 12. And that is what we are saying. Those 2 placeholding zeros are there to give us a visual indication that we need to begin by 2 significant figures to the left, or in the position 2 digits greater in significance from where we started the first answer. Then let's go. 1 multiplied by any number is that same number. That's all there is to it. Then we will begin our addition. Add. Finish up by adding the 2 results. When we add, we have 4 plus 0, 4. The same here. Then we have 3 plus 2 is equal to 5. 1 plus 1 is equal to 2. Nothing to be added to that one. It goes back exactly as it is. And our answer is not quite 12,544. But we need to make use of the decimal places. The answer will have the same number of decimal places as the total number of decimal places of the multiplicand and multiplier. We will count those decimal places. 1 there and 1 there. So we have 2 decimal places. Therefore, in our answer, we need to also include 2 places of decimal, counting from the extreme right, where the decimal point is assumed to be in a whole number. In a whole number, the decimal point is assumed to be at the extreme right, and we will count from that position 2 places of decimal. 1, 2, and there. On the next slide, we will divide 0.375 by 3, and I'm hoping that we see the 3 with the 3, and we see the 75, and we know that 75 is a multiple of 3. We will perform the division operation. The numbers are closely related, and we are quite familiar with them. We will therefore use a short division method in arriving at the answer. First of all, the dividend is a fraction and the divisor is a whole number. Whenever we divide a number by a number that is greater than that number, then we will get a fraction. This one already being a fraction and this a whole number, we are sure that this number is less than this one. Therefore, when we divide, we must get a fraction. Therefore, we will begin by showing that we are actually having a fraction and no whole number. The dividend is a fraction and the divisor is a whole number. There will therefore be no whole number in the answer. And that is why we have this 0 point here. Now 3 divided by 3 is equal to 1. And then 3 into 75 is 25. On the next slide, we will subtract 0.125 from 125.44. There we have the numbers with the decimal points vertically aligned. We may include a placeholder 0 in the region that is affected by the subtraction process. Right there will be affected by the subtraction process when we attempt to take 5 from nothing. And this 0 is also nothing. But in terms of having a digit or a numerical representation of nothing right there, I think that is the most appropriate thing to do, especially when we are subtracting or attempting to subtract something from what we have right here, which is actually nothing. Begin. We cannot subtract 4 from 2. We therefore remove 1 from the more significant position. That 1, what will happen to it? We are operating with the understanding that the place value of the more significant position is 10 times the value in the less significant position. Therefore, bringing this unit here, we will have it 10 times its size. So multiply 1 by 10 is 10. So actually we are taking 10 here. And as usual, we are not saying that 1, 0 is what we intend for 10. We are saying that it is good or maybe acceptable, or if not acceptable, usable. This 1, 0 that we have here as 10, because we are saying that when we take the 1 from the more significant position, that this 1 that we have here is 10 times the units that we have right here. So this one is taken over here as 10, and then we say 10 plus 0 is equal to 10. So we are actually taking 5 from 10. So 5 from 10, or 10 minus 5 is equal to 5. Then we say 3 minus 2 is equal to 1. 4 minus 1 is equal to 3. Do not forget the decimal point. Vertically aligned with the ones before, and those before should be vertically aligned in an addition and subtraction problem. 5 minus 0 is equal to 5, and there's nothing to subtract from the 12 that remains, and we return that 12 as it is. We may write the answer correct to 2 significant figures. Locate the second digit in order of significance by counting from the left, where we will find the most significant digit. 1, 1, 2, that's the second most significant position. Check the digit that is next in order of significance, the one that is located to the right of that digit, or to the immediate right of that digit. The digit is 5, and we are searching for figures that are greater than or equal to 5 in order that we may add 1 to the digit in question, which is this 2, which is in the second most significant position. This is 5. Any digit in the position of the one next in order of significance to the digit in question, if that digit is 5 or more, we add 1 to the digit in question. So 1 plus 2 is equal to 3. And what? The other digit to the left is not affected and return as it is. Rounding is an approximation. There is no way that we can imagine that 13 is an intelligent or correct approximation of 125 or more, because we have an additional decimal fraction there. So the number is actually a bit greater than 125. We do not imagine that that answer should properly be approximated to 13. A place holding 0 is therefore necessary to bring our number back in the hundreds. Finish up by writing the answer in standard form. The number needs to have one non-zero digit to the left of the decimal point. Count the number of places by which a number has to be increased or decreased in order for that to happen. So one non-zero digit to the left of the decimal point. So in the result, we will have the decimal point being located right here, its relative position. 0 movement, then we have 1, 2 places of decimal away. The number is decreased by 2 places of decimal. The number is therefore divided by 100, which is equal to 10 to the power of 2. We need to recover the original value of the number by multiplying by 100 or by multiplying by 10 to the power of 2. So right here we have that number multiplied by 10 to the power of 2. Why do we multiply by 10 to the power of 2? Because in order to write this number in standard form, which is actually this number in standard form, we can only have one non-zero digit to the left of the decimal point. If we have 125 here, then we have 1 point something. It means that in order to get from here to here, we have reduced the value of the number. If we are rewriting a number and we reduce its value in order that it may be the same as before, we have to increase its value. So we reduced by 2 places of decimal, dividing by 100 or dividing by 10 to the power of 2. Therefore, in the end, we need to multiply by 10 to the power of 2. A number that initially had non-zero digits to the left of the decimal point is called a large number and will be accompanied by a positive power of 10 in the end. When we have this initial number here and we have digits that are non-zero to the left of the decimal point, that number may be classified as a large number. And I'm using this as a rule of thumb, that as long as we have non-zero digits to the left of the decimal point, that is classified as a large number. And what do we know about large number? Large numbers are accompanied by positive powers of 10 in the end. Here we have the sum of two squares. We should know the two square numbers. 17 squared is 289. And I have seen this particular number on many occasions on different examination papers in some form or the other. Maybe 17 squared, maybe 0.17 squared. But for sure, on this occasion, we are seeing 1.7 squared. But 17 squared is 289 and 13 squared is 169. You will see this number 13 squared, maybe not quite often, but maybe with some reasonable regularity on CXC examination paper, especially for right angled triangles. And this number 17 is also associated with right angled triangles. Therefore 17 squared should not be such a, well, at least it should not be such an unfamiliar number. So there we have those two numbers that we have squared. 17, 289, and we square 13 and we get 139. When we square a number, the number of decimal places doubles. Each of the number that we square has one place of decimal. The result will have two places of decimal in each case. So notice that we have a single place of decimal in each case right there. But when we square a number, the number of decimal places doubles. In a whole number, the decimal point is assumed to be at the extreme right. We will begin counting from that position where the extreme right. So we will begin counting there. And why do we need to count? Because we need to write these answers to these squares, doubling the number of decimal places in each case. So in each case we will have now two places of decimal. And do not forget that in a whole number the decimal point is assumed to be at the extreme right. We will begin counting from that position, two places of decimal each. One, two, and there we go. 2.89 and 1.39. Let us take the final step on the next slide. We will go straight ahead and add the two square numbers, beginning by writing down the first one. The two numbers are in the same form. That means 3 digits and each has 2 places of decimals. We just align the digit of the two numbers and the points will also be aligned as required. When we're adding numbers that have decimal fractions, the points will have to be vertically aligned. But in this particular case, if we just throw the two numbers in, align the digits, then the points will be aligned automatically because we have same number of digits and the same number of decimal places. Put the point in and that's all there is to it. Add. 9 plus 9 is equal to 18. 8 carry 1. The one that we carried will not be left out. 1 plus 8 plus 6 is equal to 15. Write down 5 and carry 1. Do not forget, the decimal point in the answer has to be aligned with the decimal point in the problem. And finally, 1 plus 2 plus 1 is equal to 4.